Uh, yes. So let us check with the other people also. Fahad, is that okay for you? Because you're also in Texas. So 9 a.m. your time is okay for you?
Yeah, that's fine.
Because I believe for Nitin, I believe it will be better because he's in San Jose. So 2 hours later on is even going to be better for him if I let us ask him. But I think it will be okay for him.
Yeah, it will be 7 for him.
Yes. So, okay, Brolin, so let's check with the third student who is going to join in shortly. So let's check with him. If he says okay, we can finalize 9 a.m. Texas time in that case.
All right, that would work for me. Yeah.
Okay, okay. So there is one more person joining in shortly. So we'll check with him if he's okay with it because he's in San Jose in California. So let's check with him if he's okay. We will take that as the new time, starting time.
Okay. Yeah. So also, so uh, assuming you go ahead with that, then I'll say I've missed the first two classes because also today, because I didn't plan for this, I have to take these guys to the doctor at 9.
Okay.
So can I have the notes or something for me to catch up
Yes.
from tomorrow
Yeah,
or
I will.
from your?
I will share the recordings with the support team. Okay, so
Okay.
I have the recording for the last first class and this second class also. I'll be having a recording. So I will share those recordings with the support team. You contact the support team and they will hand it over to you.
Okay. Okay. That's fine.
Yes. So yeah.
Yeah.
So if you want, you can take off now since you have other stuff lined up. I will share the
Yeah.
recordings with you and then you can attend from. So next week onwards, the schedule for the class will be Monday, Wednesday, and Friday.
Monday, Wednesday, and Friday. Okay.
9 a.m. Texas time. Monday evening for me. So yeah, Monday morning, Wednesday morning, and Friday morning for you guys.
Okay. And how long is the class?
It will be anywhere between 60 to 90 minutes.
Okay. Okay. So let's say it's 10:30. Okay.
Yeah, roughly 70 minutes. You take on average around 70 minutes. So 1 hour, just over an hour, 70 minutes.
Okay. Okay. I'll attend this for like some 10 to 20 minutes because I have this guy set up.
Okay.
Uh, yeah.
Okay.
I'll log.
Yeah,
Thank you.
so I'll wait. Yeah, so I'm going to put myself on mute. So I'll wait for the third person to join and then we'll start the class.
Okay.
Okay, so I think we'll start. It's early morning for Nitin, so I don't know whether he's going to join in. So I'm going to start anyways now. Just give me a minute. I'll share my presentation. So let me know if you can see the screen.
Yes.
Okay, so we are looking at for Brolin, for advantage of Brolin, this class, the content of this training program is initially we will look at digital logic circuit design, very quickly refresher of digital logic circuits, followed by digital number systems. Then I will give a very brief introduction about FPGAs and where Verilog programming or Verilog designing stands in the entire process of FPGA or ASIC design. And then we will look at Verilog language in detail, the syntax for design, how to do this, how to design the digital logic circuits. Once you design digital logic circuits using Verilog, how do you write something called test benches and test the design? Run simulations, generate timing diagrams, analyze those timing diagrams. All of that falls under something called functional verification. So, how do we do functional verification of design? And so, Verilog design, Verilog testing, verification, and then very briefly, introduction about backend process, how that Verilog code is converted to a working FPGA or a working ASIC. Just a very brief introduction about that. So the entire focus is on Verilog, Verilog design, and but you still have to understand the other aspects of the design and the other flow. So I will touch base very quickly upon the other stuff. And the main focus of the training is Verilog and designing digital circuits using Verilog. So last lecture we started out with basic digital logic circuits. We looked at some basic gates that are involved in digital logic design. We looked at basic gates like AND gate, OR gate, NOR, NAND, NOR, etc. Then we looked at combinational circuits. So combinational circuits for digital logic design include multiplexer, demultiplexer, encoder, decoder, adders. So under adders, it could be half adder, full adder, etc. Now today we will see sequential circuits for digital logic design. So this is the current section that you see here, sequential circuits. Under sequential circuits, the very basic component of a sequential circuit is a flip-flop. So flip-flops are of different types. If you see here, the S and R or SR flip-flop is one of the basic flip-flops. The truth table for the flip-flop looks like this. When both inputs are 0, output is 0. When set is 0, S is 0 and R is 1, output is 0. When set is 1 and reset is 0, R is 0, S1, R0 means output will be 1. When both are 1, it's a forbidden state. Why? Because it will result in a race condition of a flip-flop. If S is 1, Q will try to become 1. Then R is 1, so Q will try to become 0. So there will be a race between 1 and 0. And it is possible the output will keep toggling between 1 and 0. So both inputs 1 is not allowed. Either input can be 1 at a time or both inputs can be 0. That is the truth table for a SR flip-flop. Then we have clock flip-flop. Let me pull it down here. So we have clock flip-flops. Clock flip-flops, um, in a large digital system with many flip-flop, operations of individual flip-flops are required to be synchronized to a common signal. That common signal is a clock signal. Otherwise, the operations of the system may be unpredictable. So normally you will see that flip-flop sequential design using flip-flop will have a clock, and the entire design works with respect to this signal clock, which is a common signal for all the flip-flops. Clock pulse allows the flip-flop to change state only when there is a clock pulse appearing at the C terminal. C terminal is this or this, as you see here. This is the block diagram symbol representation. Uh, we so SR the flip-flop that you see here is and the difference between these two is this is a positive edge triggered clock. flip flop, and this is a negative edge triggered flip flop. So that means when the clock signal goes from 0 to 1, that's a positive going edge of the clock. This flip flop will work with respect to positive edge. This bubble here shows an inverter. That means it's a negative edge triggered flip flop. Why? Because a negative edge triggered means the signal going from logic 1 to logic 0. That's a negative going edge, and the flip flop will work with respect to negative going edge of the flip flop of the clock. We have latches, and in flip flop, latches work with respect to. Now the difference between latch and a flip flop. You see latch and flip flop being used, terms being used here. The main difference between latch and flip flop is latches are level sensitive. That means they can also have clocks, so you can have a clocked RS latch, but they are level sensitive. That means the RS latch will work with respect to the logic 1 level of the clock or logic 0 level of the clock, not the edge, but the logic level 1 or 0. And flip flops work with respect to edges of the clock. So it's a positive going edge or the negative going edge. And latches are not preferable, flip flops are preferable. Why? Because level sensitive circuits are not, it is possible that the clock, there could be a scenario where the input doesn't change levels at all. So it is always good to work with respect to edges of the clock, where every clock edge, the flip flop, every positive edge or negative edge, the flip flop inputs will be sampled for 1 or 0, and if it is 1, the output will be 1 or 0 accordingly. So your circuit using flip flops will always be in a stable state. If you have latches in your design, there is a possibility, since it is level sensitive, latches are level sensitive for with respect to clock, there is a possibility that your latch will go into a particular state. It could be logic 1 or logic 0. It might go into that state and stay there, not come out of it. So there's a possibility the circuit gets stuck. Instead of that, if you have clocks or edges of clocks as we use for flip flops, every positive going edge or every negative going edge of the clock, the flip flop input is sampled and the output is recalculated. So there is a very less chance that the output gets stuck somewhere in logic 1 state or logic 0 state. So you should always use flip flops in your design and not latches. But digital circuit has this latches in place. Similar to RS latch, there is a D latch. The truth table looks like this. Now the truth table for latch and flip flop will be the same. Input D. Now if you take D latch or D flip flop, input D is 0, output Q is 0. If input D is 1, output Q is 1. This is how they are represented here. Now this particular D latch here has an enable signal. If you take a D flip flop, this will be replaced by a clock signal, because flip flop will work with respect to clock. So this is an enable signal that is used for D latch. Now this is what I was talking about. Latches work with respect to edges. This is logic 1, this is logic 0. Flip flops are edge triggered. This is positive edge going from logic 0 to logic 1. This is negative edge going from logic 1 to logic 0. So either your flip flops will be positive edge triggered or they will be negative edge triggered. If they are positive edge triggered, every positive going edge, so this edge, then this is the second edge, and every positive going edge, the flip flop output will be recalculated, and there's a less chance the output gets stuck somewhere. Do you understand this concept? Do you have any questions? No? Hello? Okay. So, fine. So as I was mentioning, there are different flip flop also are of different types. There could be D flip flop, there could be JK flip flop, there could be something called T flip flop, which stands for toggle flip flop. Uh, Depending on the hardware, so normally we end up using only D flip flops. in FPGAs or even in ASIC devices. Why? Because the D flip-flop uh, library is available as a part of the technology library. So normally there is only one type of flip-flop that is used on the actual chip on the hardware, and that is normally D flip-flop. So you'll end up using D flip-flops everywhere, not any other type of flip-flop like SR flip-flop or JK flip-flop or toggle flip-flop. None of these other flip-flops will be used. Only D flip-flop will be used in the library, in the design. Clock period. So this is another important concept that you have to understand, and let me shift it here somewhere. So clock period, this talks about clock period. Clock period determines how fast the digital circuit operates. How can we determine the clock period? So let us go back one cycle, one couple of slides. So this is the clock signal that you are seeing here. The clock period is the period from this positive edge to the next positive edge. So there is a edge, positive half of the clock cycle. This is the negative half of the clock cycle. Both put together from this positive edge to the next positive edge is the clock period. That is how clock period is defined. So we have to determine now what is the clock period requirement for our design. And how do we determine that? If you take any circuit which looks like this, there could be a flip-flop output that goes through combinational logic circuit. Then again it goes and you have another flip-flop connected to the output of combinational circuit. So this flip-flop will have its own propagation delay. This combinational logic circuit will have its own logic delay or propagation delay of all the logic gates combined in this circuit. And this flip-flop will have setup and hold time requirements. So the clock period, minimum clock period required for this circuit to work is this TD plus TS plus TH. If you add up all of this, this is a minimum clock period required. If your clock is such that the clock period of your clock is less than this period, then this path will fail timing, as we call it. If it is more than this clock period, your clock will meet timing. So just to give you an example, if your clock is a 100 megahertz clock, 100 megahertz clock means it will generate a T clock period of 10 nanoseconds. 1 by 100 megahertz will give you 10 nanoseconds. Now assume that this clock period, TD plus TS plus TH, this entire period is 9 nanoseconds. So the available clock period is 10 nanoseconds, the required period is 9, so your path will meet timing in that case. But on the other hand, if this particular period, TD plus TS plus TH, is 11 nanoseconds, now available is 10 nanoseconds clock period. Required clock period for this path is 11 nanoseconds. This path will fail timing. So you have to optimize it in such a way and reduce combinational logic circuit somewhere that your entire circuit, this entire delay is less than or equal to 10 nanoseconds, which is the clock period given to you. So that's how clock period is defined, and that's how clock period is calculated for a given circuit. Do you understand? Any questions?
Yeah, this is fine.
Okay. So how do you define the setup time and hold time? Uh, as in the earlier slide, we talked about setup time for the flip-flop and hold time for the flip-flop. So how do you define the setup time? Setup time is the amount of time that the data must be stable at a data pin before the clock comes, before the clock edge arrives. And hold time is the amount of time data must remain stable at the data pin of the flip-flop after the clock edge arrives. So now this is the clock. The data has to hold stable after the clock for this much time, which will be hold time. And before the clock edge, now this is also with respect to the same clock edge. It is just shown different on the different edge. Data has to arrive sometime before the clock edge comes and stay stable. So this is a setup time requirement for the flip-flop. That's how you can show setup time and hold time for flip-flops. Okay, so sequential circuits. Excuse me. So using flip-flops, we can develop different sequential circuits. The very basic form of sequential circuit is a resistor. As you can see here, this is a 4-bit resistor. Individually, it is implemented using 4 flip-flops. Each flip-flop clock is common, so it's a synchronous circuit. I0, I1, I2, I3 are inputs, 4 inputs of this resistor. A0, A1, A2, and A3 are the respective outputs of this flip-flops. So this 4-bit, using 4 flip-flops, I can create a 4-bit resistor. This is a very basic form of digital circuit, sequential circuit rather. A resistor can be a normal resistor which is parallel in and parallel out, or it can be a shift resistor, serial in and serial out. Now in this case, this is also a 4-bit resistor with it's a shift resistor. So the input is coming from, now this is the MSB part, this is the LSB part, right hand side. The input is coming to the MSB and is shifted, this data is shifted 1 bit on the right hand side on every clock cycle. So serial input comes to this D input. On the next clock edge, the output will come to this D input and then to this. So first clock edge, the output will come here. The next clock edge, this will come here. The next clock edge, this serial input will come here. And final clock edge, fourth clock edge, this serial input will come here. So clock is common for all the flip-flops. And this is a shift register. Since it is shifting right, this is a right shift register. Okay. Any questions?
In the previous slide, I understand what the hold time is. What is the setup time though?
Okay, let's go back. Can you read the setup time and ask what exactly the question is?
Like I understand why the data needs to hold after the rising edge to
Uh-huh.
read the data. But why is the setup time required? After the data has been read,
Why is the setup time that's a requirement? It's a why is it requirements? It has to be stable before on the clock edge the transition happens. Okay, so this is D input. Whatever your input, the clock based on positive. Now in this case, positive edge trigger. The flip flop will generate an output on this edge. Before this edge of clock comes in, the data has to come slightly before that and stay stable till that point. Then it is sensed as 0 or 1 properly.
all right,
If there is toggling, now if the data is not stable till that point, if there is toggling between ones and zeros, then it will be noise and that can create a erroneous output. It can create a wrong output on this clock edge. That's why before the clock edge come, the data has to come somewhere here, the setup time requirement before, and stay stable till this clock edge comes. On this clock edge, it will sense the input value, whatever it is, 0 or 1, the output will be 0 or 1. And again it has to stay stable, the D input, after the clock edge comes, and then it can change after the hold time requirement. Because if it changed before that, the clock if it changed before the whole time requirement is true, it is changing in between in this period, there is a chance the output will change again. So before the clock age comes some time, which is setup time, and after the clock age comes, which is the whole time, in that period the data D has to stay stable. So we get the correct transition at the output, and the transition stays true to 0 or 1. Okay.
all right.
So any questions on this slide? Regular register, shift register?
No,
No.
So far, so me.
Sorry, Brolin, say that again.
I'm saying so far so good for me. I think it makes sense for me.
Okay, okay, sounds good. So just like a regular shift, a regular register which is parallel load in and parallel out, and a shift register, you can combine this stuff together to create a bidirectional shift register with parallel load. So this is just one example. So this the shift register can shift right or shift left one bit at a time, or it can act as a parallel load register. So input comes in, input output gets generated at the output. I0, I1, I2, and I3 comes in as inputs. A0, A1, A2, and A3 goes as outputs. So this becomes a normal register in that case. If you use a shift register, so you can have a serial shift input which can get shifted left or right at a time. So it can you can create various combinations of these two, regular register and shift register, as per your requirement. It can be 4 bits, it can be 8 bits, it can be even more than 8 bits, depending on what your design requirement is. Okay. Another sequential circuit. So we saw registers. Now we'll see something called counters. What is the counter doing for us? The counter will help us count the clock cycles. And after a certain clock cycles are counted, there could be some output that goes high just to show that this many clock cycles are over. So, for example, you can have a up counter which will count from 0 to a certain value. You can have a down counter which can count down from a certain value to maybe 0. You can have a up down counter, combination of up and down. So it will, let's say, count from 0 to 10. If it reaches 10, then we can check if the value is 10. Then it will count, instead of going beyond 10, it will start counting downwards from 10. So you can have combination of up counter and down counter, and there can be also something called resettable counter. So again, taking the same example, if it counting up from 0 to 10, if it reaches 10, we sense that it is reaching 10, we reset the counter to 0. Again, the count will start counting upwards from 0 to 10, again go back to 0. So you can have such design in your design, you can use such counters. Even though this is showing J and JK flip flop, ultimately in your design you will be using D flip flops because the hardware only supports D flip flops in FPGAs and ASICs also. And you can have certain other enable inputs for the counters. So counters will count the clock cycles for us. Any questions on counters?
No, no problem.
No problem.
Okay. So next is a memory. So have you come across memories? And can you define, how do you define a memory?
Something that stores data like registers.
Right? Something to store your data. So how do you, when you are trying to design a memory, what are the two very basic parameters to be defined for a memory?
Size and maybe the time in between reads and writes.
What was the first one? Size, right?
Yeah.
So how do you define the size of the memory? So that's the most important part. Is first is the size of the memory.
Yeah, I think maybe just the amount of data uh, able to be stored at a particular time.
Right. Yeah. So that is how you define the memory, right? You want to store your data somewhere. That's why you are going to create a memory to store your data bits. But how do you define the size of the memory?
The number of memory elements like registers, the like 8 bits, 16 bits, that kind of stuff.
Yeah, but what is the term for that? So you take an example and explain.
So a 32-bit RAM size of
How much data do you want to store? Take some example, some number.
1 GB of data.
One,
GB.
1 KB. Okay.
Yeah.
So you want to store 1 kilobits of data, right? Or bytes of data.
Kilobits.
1 kilobits of data. Okay, fine. So how do
Yeah.
you define a memory in that case?
How many bits are in a data block, like 8-bit, 16-bit?
Okay, so let's just make it more simple. You consider 1 kilobytes of data. That is what you want to store. Just to keep it simple. Let's say I have given you a problem that I want to create a memory to store 1 kilobytes of data. How will you define a memory in that case? The size of the memory.
I think the size I would define it as so like so one memory unit. Let's say like you were saying, maybe you then one memory unit maybe carries 8 bits, so that's a byte. Let's say so
Okay.
one memory unit like allocation within your memory.
Okay.
So then the size will be equal, from what I think it will be equal to, like, so how many memory sites do you have times the number of bits that is stored in a single memory, let's say memory location, then
Right.
the single place where data is stored.
Right.
Yeah,
So
so how
yeah.
many of those you have?
Right. So the
Okay.
term used for that, yeah, you are on the correct track, and that's the correct answer. The term used, the technical term used is width of the memory and depth of the memory. Okay, width of the memory means each location is, in this case, 8 bits, if you see it on the screen. And we have such 8 locations. If you see this is a 8, 8 location is the depth of the memory, 0 to 7. And each location of the memory can hold up to 8 bits. So 8 by 8, this memory will give me 64-bit strength. Now coming back to our example. The example said that we have to define a memory of 1 kilobyte, which can hold 1 kilobytes of data. 1 byte is 8 bits. So width of the memory is defined as 8 bits here for us. 1 kilobytes we have to store. So I need 1000 locations. Roughly 1000, it's 1024 actually, but let's say 1000 locations. So 1000 will be my depth in that case. I need 1000 such locations, and each location should hold 1 byte of data, which is 8 bits. That is how I can generate a memory of 1 kilobytes, which can then hold 1 kilobyte of data. So size of the memory will be defined as width of the memory into depth of the memory. Okay.
Okay.
Yeah.
So every memory, so whatever, whenever you do design, you'll have to take this decision that how much memory space that you want. On chip memory is very costly. If you go for FPGAs or ASIC devices anywhere, anytime you design the on-chip memory, it is extremely costly. Costly in the sense you have very limited number of on-chip memory available. So you have to define, when you do Verilog design, you have to first you have to analyze how much data I want to store. Based on that, you will have to declare a memory and define you have to basically create a memory. How do you create a memory? Just like this, what we discussed. I want to store 1 kilobyte of data. Okay, I want to store 1 kilobyte of data means width is 1 byte, 8 bits. Depth will be 1000 locations. So I will define a 1000 locations memory. Each location can hold 1 byte of data. You do not want to over design. You do not want to keep or you define the memory and keep it empty, because that means you're wasting one of the critical resource on chip, which is on chip memory. So that's why you have to understand how much memory you want and design a memory only for that much space. This is how you design it. Okay, any questions on this? No. So we'll go forward. Yeah, so now you tell me that let's take another same example again. I have 1 kilobyte of memory. Now I have analyzed that and I have created 1 kilobyte of memory. So how do I access my locations? How do I control that memory? Right, that's a question I am asking you guys. How do I control my memory? Because now you have created a memory to store data. So which is correct. Now I want to store my data, and you have 1,000 locations now. Where do I store the data? How do I access my data of the memory? Or how do basically there will be two operations for any memory. You can read from the memory, you can write to the memory. Assuming it's a RAM, right? Random access or read write memory. So let's take that it's a RAM. Yes, each byte has an address. So how do I how do you control that? You're correct. Each byte will have an address. How do I control that? To have so what will be the size of the so how do I control which address where to write to the memory and where to read from the memory? Because that's the next thing I want to do after defining the memory. Yeah, that's a control signal that you're talking about, read write bar or whatever it is. It could be separate read or separate write. To that is a control signal that you whether you want to read from the memory or you want to write to the memory. But let's say I want to write to location number 500. How do I control that? Okay, so you have something called an address bus and you have something called a data bus. Right? The data bus is used to
Sorry,
transfer the data. Hello,
I didn't get the.
hello.
No, I'm saying I was away. I didn't get your question.
Okay, so I'll repeat the question, Brolin. I have a memory. Now we have defined a memory of to store 1 kilobyte of data. That means we have 1,000 locations. Each location can hold 1 byte of data. Now, after defining the memory, there are two basic operations that a memory can perform. Either I can read from the memory or I can write to the memory. Let's say I want to write to the memory. How do I control my data is going where? How do I control all that?
Oh, okay. Well, I think first we must have like like so of course we have the memory locations we talked about. So we must have a way to generate before you send or do anything. You have a way to generate the location, right? So maybe you wanna store your data in location one,
So
then
let's I will take an example. Let's say I want to try to write 1 byte of data to location number 500.
yes.
How do I do that? How do I control it goes exactly to location 500 and nowhere else?
Yeah, I think we should have like a way to generate the location number, and then like I would say like maybe a matrix. So whenever you generate this location number, then it can channel your data to the specific location number that you created,
Yeah.
something
So
like that.
what is that called? So your thinking is correct, but what is it called? In case of digital logic design or the technical term, what is it called in that case? The thinking is on the correct path, right path.
Well, I know it from my background in embedded. I would call it addressing, but
Right.
in terms of digital logic, then I don't know how to call it.
Yeah, so it's the same concept. You are addressing the memory, so you will have something called address bus and data bus. So data bus will have one. The data bus in this case will be 8 bit, because I'm going to write one byte of data at a time, because that's my memory width. I will always write one byte of data at a time, and I have to control which location it goes to. So how do I control that? Using the address bus, something called address bus. Now I want to control 1,000 locations, because I have 1,000 locations available in my memory. So I should be able to write to any location and read from any location. To do that, I need address bus of appropriate width. So how do I calculate the width of the address bus? The depth is 100,000 locations. Sorry. So overall, I have 1,000 locations, and I should be able to access any location. So the address bus should be 10-bit
A
value,
log base too.
right? 10 bit. 2 raised to 10 will give me 1024. Since this is a binary number system, so 2 raised to 10 will give me 1024. So if I have a 10-bit bus, I can generate 1,000 unique address locations or address bus values. Using the unique location value in the address bus, then I can control whether my data needs to be written to that location or read back from that location. That is how I can control the data bus. The data will also be on a data bus. The data bus will be 8 bits. Why 8 bits? Because this width of the memory is 1 byte as we have defined it. Okay, so is this clear? This memory write and memory read operation?
Yes, it's clear from my side.
And as you rightly pointed, Fahad, we can control whether we are reading from the memory or we are writing to the memory using this kind of control signal, R/W bar. When this signal is high, it's a read operation. When this control signal is low, it's a memory write operation. You can have another enable for the memory, or this is optional. One more thing that you need for any memory is a clock signal, because memory is made up of registers. Registers are flip-flops ultimately. Flip-flop needs clock. Memory will need a clock. So we'll need a clock for every memory. And one more signal that should be available for any digital logic circuit is a reset. So clock and reset are common signals for almost all the circuits in digital logic design, because I should be able to reset my design. That reset should go everywhere. So clock, because this is memory, is a sequential circuit. Sequential circuit ultimately are built using flip-flops, so I need clock for synchronous operation. And reset, because I need to be able to reset my design. So that is how I can define a memory. And as you can see here, memory are of two types: ROM, which is read-only memory; RAM, which is random access memory, or we call it a read-write memory. In the first case, I can write to the memory once and only read from it. I cannot write to the memory again. In the second case, read-write memory, I can read from the memory and write to the memory, new values. So normally, depending on what your requirement is, you might end up doing both in your design. That is how memories are defined and memories are operational. So if you have any questions, you can raise them or we'll go forward.
Everything looks good.
No
Okay,
question.
So yeah, so this is just another way of representing a memory. This is a depth of the memory, how many locations you have, and you can, using address bus, I can control the location. Data bus, I can control what data is written. Read and write can be separate control signals, or it can be in the same control signal. Read write bar. Active high is read, write bar means when the signal is low, it's a write operation. Or you can have separate control signals like this. Data buses can be a single data bus which is bidirectional. It can go in and go out, or it can be, there can be two buses. One data in bus to write to the memory, and data out bus when we want to read from the memory. So you can have a single bus which is data bus which is bidirectional in nature, so in and out using the same data bus, or data in separate bus, data out separate bus. It depends on your design. You can design it using any technique you want. So ROM, as we have discussed, ROM can be programmed once and it can be read from again and again. And ROM has its own applications. One of the common applications, if you have realized any time, is when you boot your laptop or a desktop. It remembers the date, it remembers how many peripherals are connected, keyboards and other stuff, what is the hard disk size, etc. All that is stored in a onboard ROM, which is called a BIOS ROM. And that BIOS ROM, if you have opened your laptop or desktop motherboard anytime, you'll see there is a small battery on the motherboard. So this ROM is supported by that battery, and that ROM has information about your PC. What is the date, and then what are the different peripherals connected to your motherboard, like the hard disk size, whether there is a keyboard, there is a mouse, whether there is something else, what is the memory size that on board, etc. So that is where ROMs come into picture. Yeah, so I will not go into details. ROM is basically you can program it once and just keep using it again and again. ROMs are of different types: a regular ROM, programmable ROM, erasable programmable ROM, and something called electrically erasable programmable ROM, E square ROM, which is what is very common nowadays, that your read-only memory can be programmed and erased electrically using signals. So that's called a E square ROM, electrically erasable programmable ROM. That's what is used on the boards everywhere. RAMs, as we have seen, we can write to the memory, we can read from the memory. So both operations are possible, and there could be a common signal to control it, or there could be separate signal. Data bus can be bidirectional, so the same data bus is used to write to the memory and read from the memory. Or we can have separate data buses, one going into the memory, one coming out of the memory. Any questions here?
None from me.
No.
Okay. So the next part of digital logic design, very important part, is called FSMs, finite state machines. FSM is, as we know, it has finite number of state. It is a machine, it's a digital logic circuit which can have combinational as well as sequential circuits. It has a finite number of states, and the machine goes from state to state or the reset state. A finite state machine can be represented using a state transition table. Now this is a state transition table that you see on the screen right now. Depending on the input and the current state, the next state and the output is calculated. So depending on input and current state. So there is input, there is output, there is current state, there is next state. All of that is part of the state transition table. You have finite number of states, and the machine will go from state to state depending on the input and the current state value, and the next state will be calculated and the output will be calculated based on the combination. This is a state table, as we call it, or we can represent the machine using something called a state diagram, state transition diagram. In this case, there are only two states in this machine. It goes from state 0 to state 1, back to state 0. So state 0 to state 1 will be transition based on some input value and the current state value, which is state 0, and the output will be calculated in the next state, in state 0 or state 1, depending on the input conditions. So a state machine can be represented by a state transition table or a state diagram. Either is okay. Normally, we use a state diagram to represent the state machine. Now, this is a state machine of 4 states, and this is a state diagram representing that state machine. So, how do we read this? Let's see. This is on reset, it will come to 0, 0 state. If 0/0 means first is the input value, second is the output value. If state number 0, 0, 0, if input is 0, it will stay in the same state, state 0, 0, output will be 0. In in state number 0, 0, if input is 1, it will go to state 0, 1, output will still be 0. In state 0, 1, if input is 0, it will go back to state 0, 0, output will be 1. In state number 0, 1, if input is 1, it will go to state 1, 1, output will be 0. In state 1, 1, if input is 0, it will go back to state 0, 0, output will be 1. In state 1, 1, if input is 1, it will go to state 1, 0, output will be 0. In state 1, 0, if input is 1, it will stay in state 1, 0, output is 0. In state 1, 0, if input is 0, it will go back to state 0, 0, output will be 1. So there is input, there is output, there is current state, there is next state. All 4 components are part of the state diagram. And this is how you can read a state diagram. Circles represent the states, circle and the number inside it, and the arrows will represent input and output values. So do you understand how this state machine is working looking at the state diagram?
Yep.
Okay. So as we were talking about state machines, these are some of the basic terms used. State diagram represents illustrates a form and function of a state machine, usually drawn as a bubble and arrow diagram. Why bubble and arrow? This is a bubble, these are arrows, so it's called a bubble and arrow diagram. State is a uniquely identifiable state of values measured at various points in a digital system. Next state, so state is current state. Next state means it can go to the next state in the state diagram. In the state diagram, using different input and current state combinations. Branching is the arrow that we see there, so that will be used to branch to other states. These are very two important things. So FSMs are of 2 types: Mealy finite state machine and Moore FSM finite state machine. A Mealy machine is defined such that the output is function of present state and input values. So depending on the combination of present state and input value, the output is generated in case of Mealy machine. In case of Moore machine, Moore FSM, output is based on present state only, or output is dependent on present state only. It is not dependent on the input value. So depending only on the present state, our output is calculated. That's how Moore FSM is defined. Mealy FSM, output dependent on present state. Present state is current state. Current state and input combination. Moore FSM, output dependent only on present state. So those are the 2 types of FSMs. So going back here, what kind of FSM is this? Can you analyze?
A Mealy.
Sorry,
A Mealy.
why is that?
A Mealy FSM. I am not sure I'm pronouncing it correctly. It's not a Moore FSM.
But why do you say it's a Mealy FSM? What's the reason for that?
It has both inputs and states.
There's both inputs and state. But Moore FSM also has inputs and states.
It depends on inputs, right? If it's 0, it goes to reset. If it's 1, it moves on to the next state.
Yeah, so output is calculated. Your answer is correct, but the analysis for that is it's a mealy FSM. Why? Because the output is dependent on present state and input value combination.
Yeah,
Right? For example, state number 01. If input is 0, it will go back to state 00 and output will become 1.
right.
So output is dependent on present state and input combination. If in present
Yeah,
state 01, if input is 1, output will be 0, remain 0, and it will go to state 1 1. So output is function of present state and input combination. That's why it's a mealy FSM. In case of Moore FSM, the outputs are dependent only on present state, not the input value. Okay?
right.
Yeah, so it's basically the same thing. Yeah. So I think we'll stop here today. We will continue next Monday, coming Monday after the weekend. At that time, I'm going to write to them, to the support team, that we will start at 9 a.m. Texas time.
All right. So on Monday, it's going to be 9.
9 a.m. Yes. So we'll
All right.
chat again on Monday. Have a good weekend, and we'll meet Monday again.
You too.
Yeah. Bye bye.
Thank you.